Okay, we should be recording. Everybody should see. So I thought we would begin with the convolution problem, right? And what kind of filter it is, and plotting. All right. And it's probably just best to do an example. So let's take h of t, set that equal to a delta function, minus 10. Excuse me?
Can you share your screen?
Excuse me?
You're not sharing your screen.
Ah, you're not seeing my screen. That's interesting. How about now?
Yeah.
Okay, sorry about that. So we're going to start with a convolution problem, right? And h of t is going to be a delta function minus 10 ut minus ut minus 1 divided by 10. And we'll make g of t the unit step function. Now, to kind of get a feel for what's going on, right, you probably want to plot out what everything is, right? That's our delta function. Okay, in order to draw these, the y and the time scales can't be the same version, okay? So if I see a delta function and then something in the opposite direction that starts and ends at 0, right? By now, at least I know that that's most likely going to be some kind of high pass function. All right. And then the step, right? Right. It's just going to be a step. Right. And so there's a lot of frequency right here at the step. And if it rounds it over, it'll look like a low pass. And if it detects the edge and goes back to 0, that'll be more high pass. All right. So trying to save, space on the screen, if I convolve ht with g of t, right? First thing I'm gonna get is ut convolve with delta t. Then I'm going to get minus 10 ut convolve with ut, and then I'm going to get plus 10 ut convolve with ut minus a tenth. Now, yeah, what am I going for here is I'm trying to set this area equal to 1. And what that does is it sets the gain equal to 1. If the area was larger, I would have a gain larger than 1. And if the area was smaller than 1, I'd have a gain, all right, less than 1. So really, we've got one fundamental function, right? And then we've got another fundamental function. And yeah, you can look this up on a Laplace table, but really, right, here's my two common functions. Anything convolved with delta t is going to be the function, right? Step convolved with a ramp, step convolved with step, right? The step function in the Laplace domain looks like an integrator. And so if h of t is a step and you take the Laplace and it looks like an integrator, well, then it's an integrator, and integrating a step function is a ramp, right? So we just scale and delay that, -10 RT. And then here, well, this is the same thing, except it's a different scale, right? But we know that we just sum up the delays. Here, the delay is 0. Here, it's -10, right? And really, ft equals all of those things, right? I should put a plus sign. And most people get the equations right, okay? But what happens is the plotting. I'm just going to rewrite this. So looking, right, I need time equals 0, and then something is happening at 1/10, right? So I can do 2/10, 3/10, not exactly to scale, but this should be okay. So let's do the step first, right? And that's our step function. Now we have a ramp function in yellow, right? Now, and the scale is -10. Normally we're doing ramps where it's like 1 or -1, but here it's -10, and that will give us 1 at 1/10, right? So I'm just going to draw that ramp here where, it's at -1 at 1/10. Then we have a ramp going upwards with the same slope of 1/10, right? And now we have to sum these, right? So nothing happens until time equals 0, right? But at 0, it goes up to 1, right? But then there's this negative ramp all the way to this point, right? At this point, I have a -10 slope and a +10 slope, and it evens out. All right, and so maybe I can get a flashier color here. Okay, now, yeah, there's discontinuities and things, but really it starts at 0 and ends at 0, right? And it doesn't round over that step. It never lower this slope here is infinity, and when it detects the edge, the output slope is infinity as well. Then you have a finite slope, and then the slope goes to 0 and the value goes to 0, right? So that's all leading indicators of a high pass filter, right? And here's the thing, if I had changed G of t to ut minus ut minus let's say 5/10, right? I would get this. Now, the other thing is when you look at the step response of a normal RC or RL filter, right? It kind of, right? You have that exponential decay, which, maybe you're gonna, approximate like a triangle. Okay. So all right, so I'm gonna break everybody up into rooms. And this is while I'm doing that, write down the problem. Okay. Time for breakout rooms. And again, this is just a new opportunity to make new friends. So I'm doing it manually, automatically or randomly. All right, you should have gotten, oh, I have to open. Okay, everybody should go. And we'll meet back in about 10 minutes. All right. this part of the lecture I have done 5 times.
Oh,
I don't want, I'm not trying to make it people's life difficult, but
oh, okay.
I'm not gonna go back and repeat myself.
All right. That's fine.
Because just not to be a pain, but the content is there, and I think it's really important to do the breakout rooms. So we just went over the first and order, second order. Okay, I'm not quite sure what that was. All right. So yeah, sorry, I forgot to record a little bit. But any one of those lectures, recordings where I'm talking about the first order low and first order high pass filters will be all right there at the beginning. The other labs lectures didn't have a breakout room, if I recall. Anyway. So in this case, this is the function that we're trying to fit it to, and you've got to choose the right thing. If I choose a high pass when I'm fitting for low pass, you might get an answer that's weird, but it just won't work. So again, it's second order. I can tell from 2 break frequencies and the slopes, and the phase goes from 0 to 180. Again, it doesn't really matter. I just have to set S equal to 0, and I'll get the omega naught squareds will cancel out, and I'll get the gain of the DC of 40 dB, which translates into 100. All right. I have omega naught just by looking at where it's intersecting at -90 or doing the asymptotic method. So then what remains is zeta. And in this case, it's better to try to solve for h of s where it equals to j omega, because things will cancel out, right? So what we want to do is find the magnitude when h equals j omega. So if I look this up, it's about 14 dB, which equals to 5, right? And what happens is if I set h of s equal to j omega, right, and substitute that, I really get the DC gain divided by 2 zeta at -90, right? So that's why I extract at -90. So in fact, if I have already looked up the DC gain and I just find the magnitude here, 14, I can solve for zeta and get around 10, all right? But because I can see 2 big breakpoints here, zeta will be large, right? And on the exam, I really try to make it like really obvious. Like if zeta is 1, you'll see 1 breakpoint, but that'll happen at -6 dB. But then zeta won't be 1.1 or 1.5 or even 2. It'll be a bigger number like 5 or 10. And then for underdamped, I don't make it like 0.9 or 0.8 or even, I might use 0.707 for the Butterworth, but it should be, obvious. Okay. Meaning I'm not. Yeah. Yeah. Sorry, I just read the comments. All right. So now let's look at the low pass critically damped repeated poles. So again, I look at the DC, I can see that's low pass. Over here, I can see 40 dB per decade. Over here, it goes from 0 to -180. This is all pointing towards low pass non-inverted transfer function. I find that my omega naught, it will be 100 times 2 pi. So that gives me this part, that part, and I just need zeta. And so the So here's the thing, I pull off the phase, right? But that's the magnitude I need, right? I have to make sure I'm pulling off the magnitude. And in this case, I kind of had to measure it. 33.94 dB. I convert that to a linear, solve for zeta, and I get 1.0045, which is effectively equal to 1. Now, there is just a kind of a philosophical thing that I've been thinking, is that if critically damped is where zeta equals 1, right? That's 1.0 infinite number of zeros, right? Which is effectively impossible to measure. And so in a way, nothing can be critically damped, because either it's going to be a little bit bigger than 1 or a little bit smaller than 1. And so I wonder is, yeah, they're repeated poles, but in engineering, we'd want probably a range, right? Where it's not really moving into overdamped or underdamped. But that's just my problem. Now here, now we've got an underdamped system, which is something we didn't do in the first part of the semester. But I just wanted to show you that the asymptotic method actually still works. Okay. So you just find that's the low frequency part. And I would just draw the low frequency asymptote. And then I would draw the high frequency asymptote, making that nice and parallel. And see, that intersection is right there. The intersection is not necessarily at that peak. It can be very close, right? But it's not there at that peak. So that, again, that's two ways to find omega naught, right? So again, I'm using I'm only just changing like the damping ratio, but here's 40 dB at low frequencies. That's the same gain. The omega naught is still 2 pi times 100. And we just need zeta. But notice that now when I'm here at minus 90, my gain is now 60 dB, right? And so when I solve for zeta, I'm 0.05, which is, kind of obvious. Now, here's the thing. When zeta equals 0.707, you don't really see a peak. In fact, it's minus 3 dB. Now, if it was repeated poles, that would be minus 6 dB. But with the Butterworth condition, omega naught always occurs at minus 3 dB. All right. So now we have a high pass, and we have over critically and underdamped. All right. So really, you have to recognize that it's an overdamped low pass, so you know what to go from. We know that the AC gain here, I've got it at, looks like I've measured it at 14 dB. And the phase goes from 180 to 0. So I'm actually going to pull off omega naught at plus 90, right? So since that was 1 hertz, omega naught becomes 2 pi. And then I write down whatever the gain was, minus 15.6 dB. All right. Now, the slides are getting a little hairy. So this is what I'm going to go, right, to extract to. But look at here. When omega equals infinity, this reduces to the high frequency gain which in linear terms is 5. And when S equals j omega, right, we're measuring minus 16 dB, right? We already extracted omega naught, but in this case, we're getting the high frequency gain at positive 90, right, divided by 2 zeta. And then when we solve, we get a zeta 15, which is clearly overdamped. Then we put it back here, right? We have 5, 2 times zeta plus omega naught squared. All right. Now here it's critically damped, and this is approximately 6 dB down from the maximum. All right. And again, I can find the omega naught with the asymptotic method or measuring the frequency. And again, that's still 1 hertz. So omega naught is 2 pi. And the high frequency gain is 6. So we pull this into our equations, right? And zeta is approximately 1. We have our omega naught, and we had a gain of 2. Now, here's an example where omega naught is not at the peak, right? This is omega naught, but the peak is over here. And again, if I plotted an asymptotic line this way and a line that way, you would see that omega naught is still at 2 pi. All right. The high frequency gain, 10.175 micro dB, right? That's very close to 0 dB. And so, we're going to get something a little bit less than 0.707. Okay. Now, this is a bit of a shortcut, or it's something you kind of just have to remember. But with band and notch pass filters, you can't really extract zeta at omega naught because things cancel out and you're left with too many unknowns and not enough equations. But there's something called WC, which you can kind of think of as the width of the band pass or the width of the notch pass. And you don't take that from minus 3 dB to minus 3 dB. For a second order system, you take it from 45 to minus 45. Okay, so I'll just, we'll just go through it. Right, so in this example, right, which I use an RLC circuit to generate it. So Z is 0.707, F naught, omega naught, and then I just calculate the values, right? So over here, right, that peak here in this case, right, is in fact where the omega naught is. And it's not a cutoff frequency anymore. It's not even a bandwidth. It's in the middle of the phase change. So in a bandpass filter, right, if low passes go from 0 to 180, minus 180, and if high go from 180 to 0, band passes go from 90 to minus 90, right? And so, again, I could take an asymptotic line here, they intersect, it'll give me 1 kilohertz. So what I do is in order to find minus 45, it's a little trickier, but with the cursors, it's not a problem. But I have one frequency at 1.9 kilohertz and this other frequency at 513. And I'm just wherever it's plus 45 here and minus 45 here. So so F1 and that's a typo. F1 is at 45. Okay, so F1 is at 45, F2 is at 1.95, right? I subtract them, and that's my bandwidth. Well, now I can solve that zeta is actually the bandwidth divided by omega naught divided by 2. And in this case, I get 0.713. Otherwise, you try to do it like just pick a point and use complex math to solve for it. You are in for like a world of suffering and hurting. So now in this bandpass, we can see the peak is a little bit sharper, right? So in fact, right, the damping coefficient should be smaller. And you can see that omega C right is narrower. So again, this is at minus 45, that's at positive 45. So we have 1.1 kilohertz, and now this is much closer at 9.9 kilohertz, right? I subtract that out. And I get a 1/10. Okay. Unfortunately, I guess I had just been copying the examples. Interesting, nobody claimed any credit for that last semester. All right, and now here's a really overdamped. See how much wider it is, right? So I'm here at 20 kilohertz and 49 kilohertz, which is effectively like 20 kilohertz. And I get a damping ratio of 10, right? But with the bandpass, right, it's kind of always in the middle of the magnitude. But with this, I know you have an exam, so I'm just trying to be aware of the time, right? I can take an asymptote here and an asymptote here, and the cutoff frequency will be right there, right? And I'm just going to talk a little bit about the notch, right? Is that here's the thing we have to fit it to. Now here it starts off at 0 dB, or I mean, here we have 0 phase, then 0 phase, and then right at the middle, the phase changes in 180, right? So right at that sharp change in the phase, or the smallest part of the transfer function, that's the cutoff frequency, right? You have your low frequency gain and your high frequency gain. They don't have to be the same. I try to make examples that are, right? But still, that cutoff, the bandwidth, it's the same, except here it's going to be minus 45, and this one's going to be plus 45. But really, you're going 45 degrees from wherever the change is. And that's how you get F1 and F2. In this case, you get 1. All right. But that's, pretty much the homework, and you will get some kind of plot like that. I have my open math can generate that Bode plot, and you need to find the damping, omega naught, and then whatever gains, right? And then you've pretty much solved that problem, right? And you can use this technique for the second order overdamp systems that you have to plot on the first part of the exam, which is what we did over last time. All right, so I'm just going to stop recording. And if anybody has any questions, you can stay